Good day. I'm going to do an electrodynamics problem, and the title of the problem is semi-infinite solenoid as a magnetic monopole. Okay, so I will read the text. So we consider a semi-infinite solenoid which has radius r. So here's our solenoid, and it's semi-infinite. So I'm going to draw it like that. Okay, and it has the net density of windings is given by n. That's the density of windings. Okay, and we're going to interpret the result of solving this problem. It's actually not a difficult problem to solve by itself, but we're going to interpret it, give an interpretation of it, which is a physical, it's a bit unusual because it's going to be a magnetic monopole, which we know that doesn't exist, or we think that it doesn't exist. Okay. So the first step is we consider. Okay, so our solenoid is going to be considered, the solenoid usually is something like this. Okay, and we're going to consider one winding as a ring. Okay, so that's our first, that one winding we consider as a ring. Okay, so here's our ring, and let me say that if I have the z distance z from the center of this ring, then I can easily calculate the magnetic field via the Biot-Savart law. Okay, so I first write I over C dl cross r divided by r squared. Okay, let me actually just fill you in on the notation. So that's the current, that's the speed of light. R is the vector. So basically, the line segment dl is some line segment. Okay, we're going to integrate, of course, but it's some line segment on the ring. Okay, and the distance between this line segment and the point on the z-axis where we're interested in the field. Sorry, I should state that for now we're only calculating B on the z-axis. Okay, B on the z-axis. Okay, so okay, so basically we're calculating the magnetic field on the z-axis. This dl is a small current element. Okay, and this funny r. Okay, so this script r, which is actually Griffith's notation. Okay, so I like this script, American script r. Which denotes the distance between the field point, that's the field point, and where at the source to which is being referred to. Okay, so it's an easy problem, this first part. We're going to calculate the magnetic field on the z-axis, okay, for a ring for now. So we have a ring, okay, and that's the distance z, and here I have the radius of the ring, okay. And the magnitude coming from an infinitesimal element is I divided by C. Actually, so if I take the vector product, this vector which connects the field point, that's the field point to the source point, actually other way around, source point to the field point, is perpendicular to the current element. Okay, so we can actually write dl divided by the distance, and the distance is going to be r squared plus z squared. But let me actually write this fully as I r d phi divided by c r squared plus z squared. Okay, and then what we need to do, of course, is, well, you know that from the relation of dl cross r, which is the original version of the the Biot-Savart law, you know that this magnetic field points like this, but you need this component because as we go around, the radial components cancel. At the same time, the axial components reinforce. Okay, so we actually need this component. Okay, and you know that from this is a right angle, so that particular component is going to give us the z component of the magnetic field. Okay, so, and we're going to have I over C or d phi, but we need, so this triangle here is similar to this one, and so we have r squared divided by r squared plus z squared to the 3/2, and we can integrate, and what we'll end up with is I over C 2 pi r squared divided by r squared plus z squared to the 3/2. Sorry, that's hard to read. Let me rewrite it. So B z component at coordinate z is 2 pi I r squared divided by C 1 over r squared plus z squared to the 3/2. Okay, and now we are going to be concerned with, first of all, there's one little thing here that normally this quantity pi I r squared, so that's the current times the area of the circle, and often we just say 2 magnetic moment divided by C, and still r squared plus z squared to the 3/2. Okay, now in this problem, okay, well, we're going to take z much bigger than r. Okay, so our b, if we are very far from from this object, then at least along the z-axis, we're going to get a potential which looks like 2m over c 1 over z cubed. Okay, and that's, well, that's an easy potential to recognize because it looks like a dipole, right? So that's, or it gives it's a 1 over distance cubed potential. So, and that gives the idea that that we're talking about a dipole. Now, the next step in the actual problem is to introduce a scalar potential. And the scalar potential we're going to calculate by by integrating. Actually, we should integrate h, right? So not b. Okay, so b is of course mu times h. So h z component z is 2m over mu 0 c, if you want, 1 over z cubed. Okay, so we can write it like that. And the scalar potential, okay, associated with this is going to be, so scalar potential, only along the z-axis for now, is going to be 2m over mu 0 c integral. Well, we have to start somewhere. But let's say we're going to start at 0 up to z, okay, which is where we're at, and dz prime over z prime to the third. Okay, so well, no, sorry, that's actually a mistake. Apologies. I should actually, I'm going to take infinity to be, I'm going to define the potential as, well, the work that needs to be done to bring in a so-called magnetic monopole to this distance z. So here's my, again, the ring where there's an I current going around, okay? And of course, the ring has a magnetic dipole moment which points along the axis, okay? And this scalar potential, okay, this magnetic scalar potential is, if there was such a thing as a magnetic monopole, how much work would we have to do a unit monopole to bring to the distance z. Okay, so that's actually what we're calculating here. And it's very easy to see that what we get is m divided by mu 0 c 1 over z squared. Okay, so that's what that integral will give us. Okay, so that's actually the scalar potential. And the next step, actually, I probably will make another video because I'll make another similar problem that I found in Jackson. But here, what we're supposed to do is to take the potential. So take the potential that we have and make the best fit. So basically this, you can think of this as an azimuthal problem, okay? And you have this potential, L equals 0 to infinity, AL R to the L plus BL over R squared, right? PL cosine theta. And we're supposed to fit this potential to this one, okay? Now, there's actually technically, this is actually a correct procedure, but it's going to be sort of a hand-waving procedure, at least in my opinion. Okay, so basically, if we want to fit these two potentials, then it's obvious that that first of all, there's these terms we can just take to be zero. Okay, so we will actually just forget about this, and we're going to have a b1 over r squared cosine theta, right? So that's actually, and well, the cosine theta, that's a little bit of a trick because theta is 0 along the z-axis. Okay, so that's when we recover this, and this fixes our b1. Okay, so this fixes our b1 to be m over mu 0 c. Okay. Okay, but actually I made a slight mistake here because the problem didn't really ask for this. What the problem asked for is something very similar. First, we sum up the contributions of the rings, which comprise the solenoid, okay, and then we do this procedure. Okay, but it's not going to be very different. Sorry about that. Okay, so the next step, armed with the result that this potential is m over mu 0 c 1 over z squared, we're going to do the following. So we're going to picture that we have our solenoid, but we're going to think of the solenoid as very, very closely spaced. That's not really a correct representation of a solenoid, but it's a reasonable approximation. We're going to think of the solenoid as very, very closely spaced rings. Okay, that's not quite true because the solenoid actually, so if I have a solenoid, it's more like, sorry, it's winding, but it also has a tilt, which gives a current in some other direction. Okay, but what we're going to assume is that this tilt is so small that we can approximate the solenoid by just as a sequence of rings. Okay, and if we do that, okay, first of all, we have to recall that so the total potential in this case is going to be, well, if I'm out here at distance z, okay, so this is where I'm going to take my 0, okay, so my new potential, which is going to be the sum of these contributions, well, first of all, I have to take m multiplied by the number of windings per unit length. The mu 0 c just goes along for the ride, okay, and then I have to integrate from 0 to minus infinity, right? That's a semi-infinite solenoid. And it's going to be dz prime divided by z minus z prime squared. Okay, so that's the integral which I must do to sum over all the contributions of the rings. Okay, so before we had a dipolar potential, and watch what happens here. So we're going to have mn over mu 0 c. And let me actually reverse this. So this is z prime minus z. Okay, so that doesn't make a difference because it's a square. And we're going to have 1 over z prime minus z. And that goes from 0 to minus infinity, which means that what we get is mn over mu 0 c times z. Okay, so my potential is this. That's my potential. Okay, and that's a 1 over distance potential. So it gives the feel that it's like a monopole, right? Now, the other thing is that if you really think about this, so what did we do? Let's do a little bit of a physical discussion. So basically what we did is we put these rings in sequence, which means that, well, each ring is a dipole, right? So let me say North Pole, South Pole, if you want to be magnetic, North Pole, South Pole, North Pole, South Pole, North Pole, South Pole, etc., etc. And we can say that these, since they are equal, the effect of these always cancels, but this one has no other one to cancel with. And the one at the end also doesn't cancel, but the one at the end we took to infinity. Okay, so the one at the end we took to infinity. Okay, there's actually, well, we can think of this in, there are other analogies with which to think. So, for example, if you take a real magnet which has a cylindrical shape, um, you know that a real magnet consists of infinitesimal magnetic dipoles. So you actually do have this situation, just like a polarized dielectric, right? So, a material with spontaneous polarization, you could say, right? A material with spontaneous polarization is also like this in that, but in that case you have uh, charged dipole moments. Here you have magnetic dipoles pointing in one direction, right? But effectively, you can think of this as a set of positive monopoles or north monopoles and a set of south monopoles on the bottom. So north monopoles on top, south monopoles on the bottom. Also, you can think of these as ring currents, okay? So you can also think of this as ring currents going around the side of the cylinder. Okay, and this is precisely what we did with the solenoid. So these analogies, so this, uh, so basically the statement is that with these circulating currents, you can mimic this situation, and this situation already is. You can think of this as two charges separated. So here you might have the north and the south end. Okay, north and south end. That's interesting. North end is actually the Italian section of the city of Boston. Okay, anyway, so you have north and south end, and and basically this solenoid construction gives you something similar. Okay. Now the other thing to notice though is that once I take this distance out to infinity. Okay, so once I take that distance out to infinity, then I'm going to be left only with this contribution. There are three length scales here, so we have to keep this in mind. There's one is the radius of the solenoid, okay, but that has to be very small in order for this thing to behave like a point charge or a monopole. And also we have to be um, very far from far in the sense that the distance where we are at, z, is much larger than r, okay? But we also have to make sure that this z is actually small compared to the variable that I didn't use, the length of the solenoid, because the length of the solenoid that has to be the largest, which actually goes to infinity, okay? And now, uh, when you do this, okay, um, so now we're going to again do the fit that I was talking about. So let me do the fit. So I have my potential phi z, which is mn divided by u0 c z. Okay, and we know that in general, a, a potential with azimuthal symmetry can be written as L equals 0 to infinity, AL r to the L plus BL RL plus 1 PL cosine theta, okay? But obviously, well, this is what we want to fit. So actually there's only a B0 in this case, okay? So there's only going to be a B0. And and we determine that B0 basically, right? So our potential, our overall potential fit is going to be Mn divided by mu 0 C R. Okay. And yeah, the thing is that actually there is a set of problems, and I will probably do an example and put it up for your viewing. That there's a set of problems where if you have azimuthal symmetry, okay, if you know your problem is azimuthally symmetric, you can do the problem only on the z-axis, okay? And if you have the potential on the z-axis, then you can actually do this fitting procedure that I just did to obtain the potential on the rest in the rest of the system. Okay, so it's actually one in, I think it was the first or second problem set where there was a disk. Okay, and I will do this problem and I will show you how to do it. Because here, and actually, okay, it's a more complicated problem because the disk has a very particular charge density. It doesn't have a theta dependence, but it has an R dependence, and it's kept at a fixed potential. And you have to calculate the potential or whatever. And basically, it's easy to do it along the z-axis. And once you have it along the z-axis, you can actually use this fitting procedure to get it for the whole system. Because this is we will do this in another video. Okay. Anyway, so that's definitely a monopole term. Okay. So what can we say? Calculate the magnetic induction and show that it has a source. Well, all you have to do in that case is take the H is minus gradient phi. And well, if you want the magnetic, what is called the magnetic induction, then B is mu 0 H, so the mu 0 goes, and you can definitely show that divergence of B in this case is going to be, I guess, Mn over C delta R minus R prime, maybe with a 4 pi actually. Yeah, I think with the 4 pi. Okay, so that's the essence of this problem. That's the so the essence of this problem is to realize that I'm putting dipoles together and I'm taking one side of the solenoid to infinity. And let me actually just make one. So may place a little bit of emphasis on the symmetries that we exploited here. If you take a finite solenoid like this, that is of course a cylindrically symmetrical system, right? But if I take a finite solenoid, if I take an infinite solenoid, I take this to infinity, then all I'm going to be left with is that, because we discussed how the dipoles cancel each other. And this is an azimuthally symmetric system. Okay, so for this one, strictly speaking, you couldn't use such a potential of this form. For this one, you can. Okay, so that's pretty much the essence of the argument. Okay, thank you very much.